Welcome to the final part of the Chapter 53 podcast. So, we were just talking about R-selected and K-selected organisms and how they fit in with those type 1 and type 3 survivorship curves. So, now we're going to talk about population growth models. Now, the way this works, when a population is growing, you're typically going to see exponential growth as that population starts growing. And so, this is going to be where you've got a small number of organisms, and so they go through and they're producing more offspring than ultimately are needed to just get by and sustain things, and then that greater amount of offspring produces the same amount per person. So you essentially have like 10 people each having 2 kids. Then now you've got 20 people each having 2 kids. Now you've got 40 people each having 2 kids. And so you end up with this exponential growth. So this here is showing humans, and you can see that we really started this exponential growth process, especially as we went through the Industrial Revolution. So you're talking like the 1800s, pushing through till close to today. We've been growing pretty much exponentially, faster and faster. Now this fits our selected organisms very well because they're opportunistic. When times are good, they need to rapidly populate. And because they have such short lifespans and short generation times, you might have like an aphid, for instance, that has 40 offspring. But it has that 40 offspring in like 2 weeks. And then the next generation is ready to have kids in like a week and a half or a week. And so over the course of one season, one growing season, I guess we'd say, so like, 6 months, whatever it's going to be, you might have 10 or 15 generations of aphids all able to have their 40 kids. So you can get a ridiculous number of aphids very, very quickly. So this fits perfectly with this opportunistic idea. Now the problem here is because you have this really high R value, this really high rate of growth, eventually you're expecting to hit some type of a ceiling. For most R species, what happens is they just crash at some point. Where winter comes, some of them can ultimately like burrow or somehow they overwinter, and the rest of them just die off. So they usually can't go on and on forever because something happens to their environment that pretty much just drops the bottom out from them. So the exponential model is not going to be a great model for long term. That's much more of a short term idea. The logistic model, which is going to focus on this idea of carrying capacity, which is that max amount that we can kind of stick around, that's going to be a much better model for organisms that are going to live long term, where it's not going to just be where you grow like crazy and then you crash, and then you grow like crazy. That's more of the R-selected, where it's that feast or famine type idea. With the logistic model, you've got something like humans, and you can see right now the R value of humans, the growth rate, is dropping. We're basically having fewer and fewer children, and so our growth is slowing. Now we're still growing, but at some point it looks like we will start to level off, and eventually we can get R equals 0, which means we're steady. And this is really what you expect to happen with logistic growth, is that at some point you reach this carrying capacity where you level off and you're able to sustain that many individuals, but if you have more individuals, they tend to die. You have limiting factors kick in that kind of prune the population. And if the population dips, then you've got room for more people, so they have more kids, more survive. And so in reality, if you looked at something that's logistic, it'd probably look a bit more like this, where based upon the year and how good it was and how many predators, and it'd kind of bounce up and down, but it'd kind of roughly sit around this K, this carrying capacity. And this fits perfectly with K-selected species. So species that are long-lived, that don't have a lot of organisms, so they can still grow exponentially like we did. But the issue there is it just takes a lot more time. They're not growing exponentially within one season. You're not going from a dozen aphids to what could be billions of aphids by the end of that season, literally with aphids. With humans, that's going to take a much longer time frame. So long as you give us like 1,000 years, we could do the same thing. But because we're K-selected, there's just more time involved. And that more time that's involved allows for us to kind of reach equilibrium better because we won't overpopulate as badly, so there shouldn't be as much of a crash at the end. We should be able to just kind of have certainly some bumps, but stabilize a bit better. When you do get too many people, you do tend to have more starved than otherwise would because some people get half as much as they need to live, so they still die, and somebody else got half as much and still died. Because people don't just go, you go ahead and live, I'll die, you can have all my food. So you will see that there'll still be natural fluctuations, and you have good years and bad years. I mean, that's just normal where you have a warm winter and so there might be plentiful food, and you have a bad winter and there might be a shortage of food, and so a lot more organisms die that particular year. So tied in with this, what we've been talking about is these limiting factors, these things that do change, that do control how many organisms can live in any one given time frame in that environment. Now there's two types. Density independent is one that doesn't matter how many people there are. If you've got like a forest fire, it's not like if enough deer huddle together, they'll be okay. Or if they huddle together, the fire will search them out and kill them. If you've got things like natural disasters or climate where it just gets too cold, that can kill any of the organisms. It doesn't matter if there's, 100 deer in the forest or if there's one. If it's cold enough to kill them, they die. So these are density independent. These are normally environmental. These are normally, like I said, temperature, rainfall, earthquake, volcano. Lava's going to kill you even if you hug somebody. These things are going to be density independent. Okay, now density dependent, as we wrap up, these will be things that only tend to kick in when you have a lot of people. So if I've only got a few individuals, like a few rabbits on a field, they don't have real competition with each other. There's not enough. There's a ton of food. Now eventually, if I get a lot of rabbits on that field, now we start to get where there is a shortage of food perhaps, or certainly at least not a lot of prime food, and so you start to get competition, where they've got to fight to get the best food or to get enough food. So competition kicks in dramatically when you start to have more individuals. It's not so much an issue if there's very few. Predation is the same idea. As you get more and more individuals, you tend to paint a bigger target on yourself for predators. If they're going to go after a particular species and kind of learn how to hunt it properly and to kind of train themselves how best to do it, they normally go after things that there's the most of. You're not going to try to be the best shrew killer you can be if you pretty much never see shrews. That would get you killed from starvation. But if there's rabbits everywhere, it makes sense to say, I'm going to hunt rabbits because my rabbit hunting skills will pay off a lot. And so by having a lot of you around, it makes you have a bigger target. It makes it easier for predators to go after you and try to essentially crack the code on how best to hunt you. You have stress, crowding. This is where if you cram a bunch of stuff together, you can have in some cases just pure stress hormones from being smashed together. You get things like diseases that spread well when organisms are stressed and when they're near each other, because it's easier to have transmission via whether it's waste, blood, sneezing, you call it. Any of those things will start to increase if we get them really closely crowded. And then you can have straight up waste accumulation where there's just not enough space for everybody. And I mean, that's partly something too that's density dependent, would be like not enough nests. But if you literally don't have enough places to go through and defecate, then you can have where there's too much waste that builds up. This is especially evident in aquatic organisms that are in very small habitats, like your aquarium or a puddle. As they're urinating and defecating, those chemicals like ammonia can build up in the water and become lethal. And so they essentially die because of their own waste. Now, if you're in a huge environment where there's plenty of room, this probably isn't as big of a deal. But if you're in relatively close quarters and you've got too much waste, like maybe in a burrow, like we said, the aquarium or puddle idea, then you can actually have where there's so much waste, it becomes dangerous for disease purposes, as well as just inhalation of the fumes could cause either poisoning or just a lack of oxygen. There's all kinds of stuff that can go wrong. But these only tend to be issues if there's a lot of people. If there's only one fish in that aquarium, it's probably fine. There's just not enough to cause issues. If there's only a few animals in a burrow system, it's probably fine. There's not enough to have to worry that much about waste. So density-dependent problems usually only kick in when there's a high enough population density in that area, which typically occurs after organisms have been there for a while and been successful and been exponentially growing. And then these things are what really limit you when we talk about that K, that carrying capacity. These are the guys that tend to really control that.